Hello and welcome back to yet another lecture. We're going to be continuing with Chapter 6 in Matter and Interactions. So far we've covered through 6.6, although 6.6 you're doing on your own. And now we're going to start off with 6.7, Potential Energy. And now that I know all about the length of time I have, you can expect this to come in two parts. I am setting a timer to try to make it so that none of these are more than an hour. I might occasionally miss the mark over or under, so we'll see how it goes. Okay, so in order to look at potential energy, we need to introduce a new type of system. So far, we've been looking at systems that consist of just one particle. So say we've got this ball, and the ball has been our system. Now, maybe you're throwing the ball back and forth. Now, your hands would be doing work on the ball, changing its kinetic energy, etc. Now, what if, imagine, your hands were a part of this system? How then do we handle this? So in other words, we have a system consisting of a ball and your hands. So we've got more than one object in the system. So this is what I want you to keep in your mind as we think about potential energy. All right, so far single particles. Oh man, single is just not a word I can spell today. Now, what happens with two or more? All right, and so what we're going to see is we get a new form of energy. But we can handle new forms of energy. We have been well prepared to do so. Okay, so let's flesh this out, and we will look at a ball being dropped to Earth. So typically, we've been analyzing this. Here's Earth, here's your ball, it's being dropped. It's of course not to scale. Ball is your system. And we know that as the ball is going down, so you're getting some delta y, and it has the force of gravity acting on it by the Earth. And we know that the kinetic energy is increasing. So the ball is getting faster. And this is happening because the Earth is doing positive work on the ball. So that force of gravity times that delta L. So in this case, both of these are in y, so when we were flesh out our dot product, the x and z components, of course, are 0. Okay, now let's go ahead and put some numbers to this case. So we've got a ball, we drop it, we know it gets faster. Let's say the ball has a mass of 250 grams, and unlike the little drop I did just now, we're going to drop from 9 meters to 3 meters. So in this case, the velocity is not going to drop to 0. It's still going to be mid-flight. So we want to know, what is the final kinetic energy? Okay, so we talked about intelligent plug-in chugs last time. So mass 250 grams. Want to know final kinetic energy, and delta y is 6 meters. Okay, so we need to set it up with our system. So we're going to start off with what we have been doing. We're going to use the ball as the system, and the surroundings is going to be the Earth. The initial state is at rest 9 meters above the ground. So you've climbed up, you're going to drop it out a window. I would make a reference to a dorm window, but you don't live in dorms right now, so your window. All right, and in the final state, it is falling, so it's in flight 3 meters above the ground. Very short period of time later. All right, so now we can set up our energy principle. So delta E is equal to work from the surroundings. So delta E is, of course, we have delta mc squared plus delta K ball is equal to work by Earth. All right, so where are my zeros at? Okay, so we know the Earth is doing work. That's not 0. We know that this changes, so that's not 0. However, the ball does not spontaneously explode and change in mass, so therefore the change in rest mass is going to be 0. Okay, so we've made this a little bit easier. So delta K is equal to Fy delta Y, which we talked about earlier, which is equal to minus mg, it is going down, times delta Y. So K final minus K initial is equal to minus mg delta Y. Oh my goodness, we have another 0 here. It started off at rest. How convenient is that? All right, let's plug in some knowns. So K final is equal to minus 0.25 kilograms, so the mass of the ball was 250 grams, times 9.8 newtons per kilogram, times minus 6 meters. And so we get that the final kinetic energy is equal to 14.7 joules. So kinetic energy increased just as we anticipated it would. The ball did get faster. And so yeah, the Earth did work, the ball got faster, increasing its kinetic energy. All right, old hat. Now let's look at a different situation. So what if we have the Earth, we have the ball, and we say, you know what, I want a 2-particle system. Let's include Earth in our system. So our system would be Earth plus ball. And that means that for this particular setup, the surroundings have nothing. And that means work is going to be nothing. And F net is equal to 0. There is nothing from the surroundings to do work or to bring force. All right, so this has interesting but very useful implications. So this implies delta K system is equal to work done on it by the surroundings. The mass isn't going to change. So delta K ball plus delta K Earth is equal to 0. But wait a second. We know this isn't 0, not 0. This I'm willing to grant you, but this is clearly not 0. We just calculated it. So what that means is something is missing. So when in physics you come up with a contradiction, like a contradiction to the energy principle, you shouldn't say, oh, the energy principle is broken. No. The energy principle is likely not broken. It's likely that you just haven't accounted for all the forms of energy in your system. We need potential energy. And because we now have a system consisting of 2 or more particles, this is something we need to contend with. And potential energy is the energy of interacting objects in the same system. So remember, we are in energy principle land, not momentum principle land. Internal energy interactions don't cancel out the way internal forces cancel. Okay, so in the ball plus earth, we have two interacting objects. So the energy of our system is equal to the mass of the ball times c squared plus the kinetic energy of the ball plus the mass of the earth times c squared, make that a nice capital E, plus the kinetic energy of the earth plus the potential energy. So potential energy is typically denoted as a capital U, ball plus earth. All right, so just a quick aside on potential energy notations. So potential energy in basically all physics and more advanced textbooks is denoted as a U. In a lower level textbook like a physical science textbook, you may see it denoted as PE. But this is the more standard of the two conventions, but just know you might see this too. Okay, so end aside. Whenever possible, I want to try to just familiarize you with other notations that we don't use in class, just so that you're not surprised when you see them. And for those of you teaching high school physics, you may have to use the PE notation. I used it when I taught physical science. All right, so the potential energy between the ball and the earth is related to the change in separation. So if you took a high school physics class, I think you know what this is building for. So when you start out, when you have a ball that's high above the ground, you have a lot of potential energy. As it falls and the kinetic energy increases, the potential energy decreases. So as it gains kinetic energy, it loses potential energy. So I'm giving you a lot of potential, and now I am giving it a lot of kinetic. I should really just drop it. There we go. Okay, and again, that works with the energy principle. We need it to balance out nicely. So delta K ball plus delta K earth plus our missing factor, delta U ball earth, is equal to 0. So there is another way to think of U. By this I mean that U. U is internal work. So delta K ball is equal to work by the earth for our first setup, and delta K ball plus minus work by the earth is equal to 0. And from here we can see that delta U is equal to minus work by the earth if we include it in the system. Pretty nifty, eh? So the approximate change in potential energy near Earth's surface from gravity, delta U grav, is approximately delta mgy, where really y is the factor that's changing. So, and this is not the potential between the earth and the object, but the change in potential energy, so it requires a delta y. And we'll get into the differences between the two. So going back to our example with start a new sheet of paper. For our 250 gram ball, so we know that our delta y is equal to, and it starts at rest, so the system now is the ball plus Earth, and our surroundings, nothing, initial, starts at rest, final, ends not at rest. Okay, so you would not need to rewrite this if you were doing a problem looking at two different scenarios. Okay, so let's set up our energy principle. I'm going to drop the first step. So we have delta MEC squared plus delta K Earth plus delta mass ball times C squared plus delta K ball plus delta U is equal to 0. All right, so where that was work. Where are the rest of my zeros? Okay, rest mass energy of Earth doesn't change. Rest mass energy of the ball doesn't change. So a little bit easier. Great, I love easier. So we have 0 plus K ball final minus 0 for the initial kinetic energy plus delta mgy is equal to 0. K ball final plus 0.25 kilograms times 9.8 times minus 6 is equal to 0. We can move this over to the other side, and we get that the kinetic energy of the ball final is equal to 14.7 joules. Same thing we got last time, but using a new method. So when you learn new methods, it's good to repeat something where you know the answer, just to confirm that it, all makes sense. And this does make sense. The ball increased in kinetic energy. Now, we did make a very interesting and very appropriate assumption. We assumed the change in kinetic energy of the Earth is approximately 0, which is really okay because the Earth was only slightly displaced. It's really the ball that was noticeable in this particular problem. So to sort of wrap up our introduction of potential energy, 2 key points. Systems of single particles have no potential energy. And systems of 2 or more particles will have potential energy. So, just a question to ask yourself when you're setting up your energy equations: have you accounted for every single type of energy for that system? If that system has 2 or more objects, potential energy needs to be in it. So like I said, in these chapters, our energy principles are just going to grow as we learn. It's kind of like, what you do in kindergarten. The more you know, the more you can read. It's great. All right, so let's look at the internal energy in a multi-particle system. So we want to extend our idea beyond just the Earth and a ball. And let's say that there are 3 charged particles being worked on by the surroundings. So we've seen some setups like this before. So we have our 3 particles. Here they are. Let me put them all. So we have F1, F3, F2. So this is M1, M3, M2. Now, we're not done. So all of these particles are forcing on each other. So we have F1, 3, F3, 1. All these are vectors, by the way. F3, 2, F2, 3, F1, 2, F2, 1. So, internal forces. Have been denoted with a little f, and external forces have been denoted with a capital F. All right, so as I said before, we are in energy principle land, not momentum principle land, so we have to consider these internal interactions. Okay, so let's go ahead and write out our energy principles. So I'll keep this here so that I can bring that in to refer to again. So the change in energy for particle 1 is going to be equal to F12 plus F13 plus F1, capital F, from the surroundings, dotted with delta R. This is equal to work 1 internal plus work 1 from the surroundings. And it follows delta E2 is equal to F21 plus F23 plus F2 from these surroundings, dotted with delta R, is equal to the work 2 internal plus the work from the surroundings, delta E3 is equal to F31 plus F32 plus F2 from the surroundings, dotted with delta R3, is equal to work 3 internal plus work from the surroundings. Okay, so, and this all comes from this picture here. All right, so adding up the 3 particles, we have delta E1 plus E2 plus E3 is equal to work internal plus the work from the surroundings. So this is the internal force. This is the external force. So, and we can see these here. So here are the internal forces, and here are the external forces. All right, so let's separate out internal and external forces. Or sorry, internal and external terms. So delta E1 plus E2 plus E3, so the change of all three of these, plus minus work internal is equal to work from the surroundings. And now we see a new relationship falling out. So this, of course, responds to kinetic. And this is delta U. So delta U is equal to minus work internal, as we said before. So the change in potential energy of a system is defined to be the negative work done by the internal forces of the system. So I'll write that out. Delta U is potential energy, well, change in, or internal work. So delta U is equal to U12 plus U23 plus U31, etc., depending on how many objects you have in your system. So for every pair of interacting objects you have within a system, you will have potential energy between them. So if we had these three pens in our system, we'd have the potential energy between orange and green, the potential energy between blue and orange, and the potential energy between blue and green. Okay, so let's write out the energy principle. As a system of interacting particles. So the energy of our system is equal to m1 c squared plus k1, so this is our three particle system, plus m2 c squared plus k2 plus m3 c squared plus k3 plus u12 plus u23 plus u13 plus however many. We could also write delta E1 plus E2 plus E3 plus so on and so forth plus delta U12 plus U13 plus U23 plus so on and so forth is equal to work. So that's how you account for a multi-particle system. So within this class, we're going to be dealing with systems we can easily calculate by hand. Obviously, very complicated system you would bring in a computer program. All right, so to not make the same mistake as last time, so this wraps up 6.7. I'll record the second section of this lecture, 6.8, as a separate video.